So these shapes are all examples of things called polytopes. So a polytope is basically a sort of generalization of a polyhedron. Okay, so what we're looking at here are these shapes like a polyhedron. For example, this cube here. This is a 3D shape. You can see it has vertices, edges, faces. And so it's a 3D shape. But a polytope is the same kind of idea, but it can be in higher dimensions. And so I'm really interested in four-dimensional polytopes. Now, we can't really see four-dimensional polytopes properly because our space is just three-dimensional. However, we can see 3D shadows of these 4D polytopes, and this is most of the things that I'm drawing here. For example, this is a model of a four-dimensional cube. This is a sort of 3D shadow of a 4D cube. This is called a tesseract. Now, let me just quickly explain. I'll give you a sort of 1 minute introduction to high dimensional space. So this is a cube. This is a three-dimensional polytope. We could say this is a three-dimensional cube. We could say this is a two-dimensional cube. This is a square, okay? So this is an example of a two-dimensional polytope. You can just go in two different directions, forwards and to the right, and it just has vertices and edges forming its boundary. Now, if we want to turn this two-dimensional cube into a three-dimensional cube, we move it in a direction perpendicular to the stuff we already have and see what kind of shape gets swept out. So basically we can just clip this on, and that makes our three-dimensional cube. Now, if we get the same kind of thing and we were able to shift this cube in another direction that's perpendicular to all the ones we have, then we can get a four-dimensional cube. So this isn't really a four-dimensional cube, it's a sort of 3D shadow of it, and there are many different 3D shadows of it, depending on kind of where you're looking at it from in 4D space. Much like if you have a 3D cube, and you sort of like a wireframe of it and you shine a light behind it and look on a wall, you'll see that the kind of 2D shadow that you get can really look quite different depending on orientations of stuff. So anyway, this is made out of zometools. You can see you can just clip these things together. And so whereas this 3D cube here has vertices, edges and faces, this 4D cube here has vertices, edges, faces, but it also has these cells here. So it actually has 8 cells. It has 1 cell in the middle, and then it has 6 cells around the outside, 1 for every face of the dice, and another face that's sort of the outside, if you like. Yeah, if that confuses you, take a big white ball and draw this shape on it. Now, okay, I'm drawing this on a piece of paper. I wish this was drawn on a big white ball, because if this was drawn on a big white ball, you'd see that it has 1, 2, 3, 4, 5, 6 faces. And if you imagine that this is sort of a graph or made out of something elastic so you can stretch it around, you can see that this would basically have the same shape as a cube, right? You could pull the vertices all the way back so that it was really uniformly spread across the ball. But we could sort of topologically equivalently push all of the stuff into our sight, and then basically this outer thing would be the 6th face. So that's how it looks in 3D with the 3D cube with this thing here. Like, imagine that this was drawn on a ball, so it'd be a little bit curvy, but it would still be the same sort of topologically. You know, if these 8 vertices were all placed on a sphere, and then we, instead of having straight blue edges, we could have these sort of shortest path lines on a sphere connecting them, and then you'd see that the sort of sick face would correspond to the stuff on the back of the sphere. And basically this is the same thing with the hypercube, but in one dimension higher. Anyway, I don't want to get too much into all of these details. I just want to show you some of these beautiful polytopes. So you've got to love the hypercube or the tesseract. It's a sort of gateway into this 4D geometry. It's a beautiful thing to try and visualize, try and think about stuff like what it would be like to walk around in it. That's always a fun thing. But there are various other lovely polytopes. So in 3D, the cube is an example of a regular 3D polytope, because basically, roughly speaking, all the vertices look the same as all the other vertices, all the edges look the same as all the other edges, all the faces look the same as all the other faces. Okay, here's another example of a 3D regular polytope. These are also called platonic solids. This one's called the icosahedron. It's another beautiful one. Incidentally, this is called the small stellated dodecahedron, and it can also in some ways be regarded as a platonic solid. Okay, or so I've heard. I to be honest, I don't really understand the intricacies of these things, but it's a matter of definition, right? Are you going to allow these kind of star-shaped things? And most people don't. So most people would say, no, this is not a platonic solid. There are only 5 platonic solids: the tetrahedron, cube, octahedron, icosahedron, and dodecahedron. But if you allow these star shapes, then you get a few more. So this is discussed in Coxeter's book, Regular Polytopes. Okay, so let's carry on with the 4D stuff, because it's really cool. Now, take a look at this shape here. Now, just for a second, pretend that all this stuff in the middle wasn't there. Okay, so if we only had the green vertices and these the green edges and these 4 outer vertices, that would be a tetrahedron. Okay, so if I sort of try and cover up the stuff in the middle, this is a triangular base pyramid, aka a tetrahedron. And this is one of these platonic solids. It's the simplest one. In a way, it's the simplest 3D shape. Now, once we go to 4 dimensions, basically, there's something else that's sort of corresponding idea in 4D, and it's this. It's sometimes called the 5 cell. Okay, so the recipe for building these kind of structures is pretty simple. So, a triangle, we could say that this is like a sort of 2D version of a tetrahedron. Now, if we add a sort of vertex and make a pyramid, so remember this vertex has to be sort of above the original triangle, so it has to be outwards from it in the 3rd dimension. Well, now we have this, which is a tetrahedron. Actually nicer to draw it from above, like this. Okay, so this is what a tetrahedron looks like from above. But really this point here is sort of elevated in the 3rd dimension. So whereas these 1, 2, 3 would live in the plane, this 4th vertex is a bit higher up in the 3rd dimension. And similarly, if we take our tetrahedron and then we add another vertex, this is sometimes called forming a pyramid. So we add an extra vertex, but now imagine it's sort of elevated above the tetrahedron in the 4th dimension, and it's connected to all of the others. And we get this shape, which is basically a 3D shadow of what we could call a 4D tetrahedron. We could call it a 4D simplex. Simplex is the fancy name for these tetrahedra in different dimensions, if you like. And it's called the 5 cell. Okay, that's another name for it. Why is it called a 5 cell? Well, basically because the number of 3D cells it has. Okay, so polytopes, they have vertices, edges, faces, but also have cells, the 3D parts, and it has 5 of them, okay? One here, 1, 2, 1, 2, 3, 4, and then 1 for the outside, okay? So the 4D cube, or the tesseract, this has 8 cells. I showed you those before. And this thing here, it's like a 4D version of a tetrahedron. It has 5 cells. All right then, what else have we got in this lovely collection here? Well, this is another, actually, and maybe I'll show you this one. This is something called the 16 cell. So this is another one of these regular 4D polytopes. And you can actually basically get this by taking your tesseract and then drawing a vertex in the middle of each of the 8 cells, and then connecting 2 vertices when there's a sort of 2D face which is separating them. So imagine like there's a vertex hovering in there because there's a cell at the top. There'll be a vertex hovering in there because this is a cell. And then these two have this bounding face, so we join them. And if we do that all the way, we get this, which is the 16 cell. So this is one way you can visualize the 16 cell. And if you look carefully, it's maybe not very easy to see, but basically it's what you get if you take an octahedron and then you add 2 new points, the gray and the blue one here, and each of those points are linked to every vertex of the octahedron. Now here's another sort of 3D shadow of the 16 cell. It looks simpler, and basically it's because we're looking at the 16 cell now from an angle which basically makes this point here and this point here appear in the same place. So let me quickly show you a way to draw an octahedron that I really like. So firstly, let's draw a tetrahedron. There we go. And so now what we're going to do is something called rectifying it. So we're going to add a vertex in the middle of every edge, like this. And then we're going to think of what kind of polytope has this vertex set. So if we just sort of join together 2 of these vertices, when the corresponding edges meet at a vertex, like these guys meet over here, then we are going to get this lovely shape here. And you can probably guess what it is. And so this is sort of showing you that if we rectify a tetrahedron, we get an octahedron, and so this is like the sort of 3D version. And then if we pump the dimensions of everything up by 1, we get this beautiful shape here. Okay, so what we're really doing here is we're starting off with our 5 cell. Think about this big 5 cell here with these 5 black vertices. It's basically just a big version of this little baby here. So this is the big version. But then, we're sort of adding these vertices in the middle of the edges. And, if we were just looking at the shape that was formed by that, we'd be having the shape that's formed by these white vertices. And that's called the rectified 5 cell. So you can search for that on Wikipedia. There's a web page on it. I actually think it's a really amazing shape that hasn't got as much attention as I think it deserves. I intend to study this a lot more in the future. But you can see that it sort of lives inside of this 5 cell, and there's all sorts of things I really love about this. Like you can see that, for example, we have a little 5 cell at the top, and it's touching this rectified 5 cell, which is this white thing in the middle, and they're sort of sharing this this 3D cell here. So, like this octahedron in the middle of this tetrahedron has these like 2D boundaries with these little tetrahedra on the outside. So if you like, what we've really done is cut up our tetrahedron here into 4 pieces, an octahedron in the middle, 5 pieces, an octahedron in the middle, and then 4 tetrahedra around the outside. And something similar is going on here, although I'm still really trying to get my head around it. But 4D geometry, at least for me, I don't find it easy, but I do find it fascinating. And the idea that you can have 2 of these sort of 4D polytopes next to each other with a 3D boundary, I find that just like really, really interesting. I think if one looks at this for long enough, one can start to see stuff like that. What else have we got here? We've got this. This is the 24 cell. I absolutely love this shape. I'm not going to say too much about it. I've basically had this video on perfect shapes, and I talk about this so much because I basically had a year where I was completely obsessed with this shape. It's really, really nice. It's one of the most important. It's one of the most important shapes in geometry, I think. Okay, this is another sort of 3D shadow of the 24 cell. It's a little bit inferior to this in some ways because it has this issue that some of the vertices appear on top of each other. To understand this issue, it's the same thing that is a problem here. So to understand this kind of phenomenon here, like what we have here, and also in the 24 cell, where we have like vertices appearing on top of each other, think about this 2D shadow of the cube. And you can imagine if the cube moves a bit, it could basically be that this vertex appears on top of this vertex. And then you would look like you'd only have 7 vertices on the picture. But there's actually 8. It's just that you're looking at it from a weird angle where, where like 2 of the vertices appear on top of each other, and it looks like there's a hexagon around the outside. So yeah, that can happen sometimes. So that's the kind of similar kind of thing to what's happening here, basically, that you've got 2 vertices appearing on top of each other because of the way you're looking at this from the 4th dimension. Okay, my phone's running out of memory, so let me very quickly talk about the rest. This is one I absolutely love. This is what you get if you take the cube here, and then the tesseract, and then you just add a vertex on the middle of every edge, and then you connect those up. You get this. So it's sometimes called a rectified tesseract or a truncated tesseract. Coxeter calls it truncated. Most people call it rectified. So if you look on Wikipedia, that's what that is. Now, another one that I'm starting to really love a lot, if you get the 5 cell and then you do the same kind of thing, so you sort of rectify it, so you add a vertex on the middle of every edge. This isn't very well studied. It's called the rectified 5 cell, and it's in here. Okay, so what I've done here is I've got the original 5 cell, and I've sort of added these extra edge midpoints, which are these white vertices. So really, if you can, like, try and ignore the stuff on the top here. Just focus on the stuff made by the white vertices, and that's basically what you could call the rectified 5 cell. But really, I'm drawing the rectified 5 cell inside the original 5 cell, if you like it. So I started building out this shape. So basically what I'm doing is, like if you have 2 interpenetrating tetrahedra, that makes this shape called the stellar octangular. And so I'm trying to do something a bit like that, but a kind of 4D analog of it. So you can imagine if you get rid of all the yellow stuff and you built another tetrahedron shaping the other way, you could basically have get rid of all the yellow stuff except just this central line to this central black point. And then you can imagine basically 2 5 cells that share that common point in the middle. And this is something related to what I'm making, but also I want to have these these extra yellow bits and these midpoints and things. So I'm not quite sure exactly how principled this is, but let's see where this goes. So here's the result. It's 2 5 cells that are going through each other, very much like the stellar octangular in 3D. So you can see that there's some very interesting shape being formed in yellow in the middle. Now I'm wondering if this corresponds to the intersection of these 2 5 cells. And a bit of Googling tells me that there's something called a bitruncated 5 cell, which that might correspond to, but I'm still trying to understand more about this stuff. At any rate, I just feel so grateful to, live in a world where we have the ability to think about things like this, and we have these amazing things like these zometools. I mean, it just makes me very happy. And finally, we have the 120 cell. Absolutely beautiful shape. I talk about all of these things a lot more in my video on perfect shapes. And that's really something I put a lot of effort into. So if you're interested in this stuff, you might want to check that out. And the work continues. The more encouragement I get with stuff like this, the better. I feel like these polytopes, maybe they're a little bit of a throwback. Maybe not as cool as category theory, but they are so beautiful if one really gets into it. And I'm continuing to learn more and more about them, especially these Coxeter groups, just fascinating. And watch this space.